We are all drawn to beauty and mystery. In reality, the most fascinating landscapes are those that we can't see the end of, those that we can't understand. And nothing is more elusive than stars. Nothing stirs our soul like them, one-of-a-kind companions for night-long travels in ancient times before the development of electricity. Since prehistory, when the first representations of lunar cycles were carved in caves alongside images of animals and hunts, men have been drawn to these gleaming objects in the night sky. Another fantastic example of this insatiable desire for stars is the myth of Icarus, who attempted to reach the sun with his wax wings but tragically lost his life. Hundreds of astronomers who study these majestic celestial bodies are motivated by a strong desire to understand stars. But, as the Greek story illustrates, sometimes our tools are insufficient to complete our job, and we want a technological breakthrough to advance our studies. What was the first outstanding instrument that marked an incredible advancement in physics research? The telescopic lens. When did it first appear? Who was the first to utilize it to examine stars and planets? What has been its evolution over the centuries? What are the most significant devices today? Are they truly distinct from earlier models? These and other topics are the focus of this movie, so stick with me and prepare for a fascinating voyage through the history of telescopes. This gadget is a complicated system of lenses and curved mirrors that can be used to observe and investigate distant objects' radiation. It's the major thing that allowed us to look up above the sky, towards those enigmatic bodies that occupy the night's blackness. However, its usage and structure have evolved significantly over the years. As a result, we must examine the origins of this formidable instrument in order to comprehend its evolution. What is the first evidence of the telescope's existence? The first extant document is a 1608 patent application by Middelburg spectacle manufacturer Hans Lippershey to the Dutch government for a refracting telescope with the famous description for seeing things far away as if they were nearby. The true creator is unknown, but mention of it spread throughout Europe. And do you know who was trying to study stars and planets at the time, uncovering astounding mysteries that led to the development of the scientific method? Galileo Galilei was a scientist. The Tuscan astronomer, born in Pisa, was first obliged to study medicine by his father, but after witnessing a geometry lecture, he convinced his parents to let him devote his life to mathematics and natural philosophy. He proved to be excellent, and he was appointed chair of mathematics in Pisa in 1589. After that, in 1592, he proceeded to Padua to teach mathematics, geometry, and astronomy. Galileo was considered the first true physicist in history, and based on Lippershey's description, he was able to build the first telescope for astronomy. The Dutch, in fact, exploited this gadget for military objectives. How did the Tuscan scientist find out about the telescope? Galileo Galilei was in Venice in June 1609 when he heard about the Dutch perspective glass, a military spyglass that made distant objects appear closer and larger. Galileo claims that he solved the challenge of building a telescope the first night after returning to Padua from Venice and built his first telescope the next day by placing a convex lens in one end of a leaden tube and a concave lens in the other. Marcantonio Mazzolini, an artisan from a clock-making family, assisted the astronomer in his later projects. This is the earliest example of collaboration between natural sciences and industry, intended as a partnership of theoretical knowledge and technical abilities. What were the features of Galilei's telescope? Unlike Lippershey, Galileo discovered a means to reconstitute the direct image of distant objects. What does it imply? These technologies relied on geometrical optics, specifically refraction. They were able to magnify what they were pointing to by using a lens, but the image was flipped. If the original model only had 2x or 3x magnification, Galilei's model had an outrageous 23x magnification. These powerful devices aided in many significant discoveries. The famed astronomers spotted Jupiter's satellites, hills and valleys on the Moon, Venus's phases, and sunspots. Imagine his surprise when he realized that planets and satellites were not ideal things, as ancient models implied, but were more like our Earth. These discoveries were critical in demonstrating the superiority of the sun-centered Copernican system over rival Earth-centered systems, such as Ptolemy's. Furthermore, Galilei was the first to use the name telescope, which derives from the Greek words tele, far, and scopion, to look a great definition for an equipment that aids in the observation of distant objects. Although their significance cannot be overstated, these instruments required significant upgrades, which were made by the legendary Johannes Kepler. He proposed the building of a telescope with two convex lenses in his catoptrics in 1611. The advantages of such a structure were highlighted by the British William Gascoigne, but it was not until the middle of the 17th century that Kepler's telescope became widely used, not so much because of the advantages highlighted by Gascoigne, but because its field of view was much larger than that of the Galilean telescope. What was the first significant discovery made with a Keplerian telescope? Christian Huygens found Saturn's brightest satellite, Titan, in 1655. These celestial bodies are currently being examined because they may contain new forms of life. Let us now discuss the primary issue with the Keplerian telescope. Chromatic aberration was present in the photos produced by this instrument. What does it all mean? Lenses have a variable refractive index for each wavelength of radiation that correlates to a different color. As a result, the various components of light diverged in somewhat different directions, and the resultant images were identical to the genuine item but slightly misshapen. How was it feasible to resolve this issue? The only thing that could be done was to construct long structures along the focal axis to decrease chromatic aberration. This sort of telescope was known as aerial, and one of Huygens' efforts reached an extreme length of 64 meters. As a result, these items were neither feasible to use nor to construct. Modern telescopes, on the other hand, are quite different. Do you understand why? Refracting telescopes had a limitation. Their focal diameter could not be increased endlessly since it is difficult to mechanically manufacture a huge lens and keep it horizontal with only lateral support. In the second half of the 17th century, physicists like Isaac Newton realized that using curved mirrors to magnify distant objects was more practical because they could be sustained more easily. This was the beginning of the era of reflective telescopes. Based on his theories of refraction and color, Isaac Newton concluded in 1666 that light could not be refracted through a lens without causing chromatic aberrations, despite incorrectly concluding from some preliminary experiments that all refracting substances would diverge the prismatic colors in a constant proportion to their mean refraction. Newton concluded from these experiments that the refracting telescope could not be improved. As a result, he began conducting reflection experiments and discovered that the incident angle is always identical to the reflected angle for all colors. Chromatic aberration was solved. Newton's first telescope, built in 1668, consisted of a circular primary tin and copper mirror and a diagonal secondary mirror that reflected light at 90 degrees towards the observer's eyes with minimal blockage. Cassegrain created further models that featured a secondary hyperboloidal mirror to reflect light. Later in history, in the 18th century, an unexpected figure changed the history of telescopes: William Herschel, a former musician with an interest in astronomy. Around the year 1774, he began to spend his spare time building reflector telescope mirrors. He was able to construct an extraordinary mirror with a focal length of 40 feet, 12 meters, and a diameter of 49 inches, 120 centimeters, at his new home, Observatory House in Slough, England. The size of the mirror is significant because the more light that can be captured to generate a good image, the larger it is. With this enormous telescope, he discovered Uranus and catalogued more than 2,500 nebulae. However, the first huge telescopes were not developed until the second half of the 19th century, when Foucault's study on the manufacture of mirrors by the deposition of silver on glass surfaces aided in the development of more sophisticated research apparatus. What were the novel features of these instruments? The silver layer was far more reflective and durable than the finish on speculum mirrors, and it had the advantage of being removable and redeposited without affecting the form of the glass substrate. With the passage of time, telescopes grew in size, eventually reaching a diameter of 10 meters. The LBT in Arizona is the tallest, almost 11 meters, followed by the GTC in Canarias and the Keck in Hawaii. Furthermore, in 2010, ESO, European Southern Observatory, initiated a project that would result in the construction of one of the most amazing telescopes ever. It will be called the ELT, Extremely Large Telescope, and will have a diameter of 39 meters. Absolutely insane. Do you know why all of these advanced research telescopes are scattered across the globe? And why do scientists want to build them on ridges or hills? Light pollution is currently a problem for researchers, and it is unquestionably preferable to see stars and planets far away from the lights of major cities or highways. Furthermore, high altitudes are preferable since there is less atmosphere between the sensor and the star. Why is the atmosphere hazardous to astronomical observations? Because air can swiftly change temperature and density, the light radiated by the celestial object is altered. Turbulence causes stars to twinkle in the sky, which is horrible for researchers since photos get severely distorted as a result. To address this issue, a new branch of optics called adaptive optics emerged in the 1980s. It is based on hundreds of corrections every second to compensate for the effects of rapidly shifting optical distortion caused by turbulence in the Earth's atmosphere. How are these changes made? Adaptive optics works by sensing wavefront distortions and compensating for them with quick changes in actuators applied to a tiny deformable mirror. Finally, scientists made another astonishing breakthrough. They were able to launch telescopes into space. Why do we launch them into space? The major reason we send telescopes into space is to avoid the Earth's atmosphere and acquire a better view of the planets, stars, and galaxies we're studying. Our atmosphere works as a protective blanket, allowing some light to get through while blocking others. These remarkable equipment, in reality, do not only examine visible light, but also other frequencies of electromagnetic radiation such as UV rays, microwaves, infrared rays, and gamma rays. Hubble, the most famous space telescope, has taken the largest photo of deep space, showing the oldest objects visible from Earth. NASA's long-term goal is to replace this remarkable equipment with a more modern one called James Webb.